today, K is going to be a finite field, FQ. Q is odd. We're going to stick with unitary groups and the function field analogs of unitary Shimura varieties, and so we need the function field analog of a quadratic imaginary field. So that's going to be a finite étale cover x prime to x of smooth, projective, geometrically connected curves over our finite field K. So you should imagine, of course, that x is the rational numbers and x prime is a quadratic imaginary field. Or a little more precisely, that's really their function fields, which I'm going to call f prime and f. So some degree 2 extension. And the non-trivial automorphism is going to be sigma. And similarly down here. Okay.
Is there a missing word?
Fix finite étale cover function field. Geometrically connected. Thank you. Thank you. Okay. Okay, we're still going to be working with automorphic forms on a quasi-split unitary group. And the quasi-split unitary group is the exact same one that we had last time, just over the function fields. So let's fix a d at least 1 and hd equals udd. This is going to be the quasi-split unitary group. Yep.
In your previous talks, you justified working with unitary groups over orthogonal groups because you always had a Shimura variety. Are similar considerations?
You're asking, in other words, is everything that I'm going to say in this lecture known if I switch to a symplectic orthogonal dual reductive pair? And the answer is everything is expected and nothing is known. It's harder, actually, in the orthogonal case. I mean, in some... I mean, I'm going to write down, eventually, a moduli space of unitary shtukas, Hermitian shtukas, and the definition of that makes sense in the same way in the orthogonal case, and the definition of the cycles makes sense in the orthogonal case, but when you actually try to sit down and prove things, it's actually quite a bit different. But there isn't an issue of like the PEL type versus only Hodge type. That's not a thing here at all. So, quasi-split unitary group. So this is a reductive group over F, our function field. Of isometries of F prime, take 2D copies of it, endowed with the skew Hermitian form. Defined by our favorite skew Hermitian 2D by 2D matrix. So in particular, just to be totally explicit, the F points are all the points in GL2D of F prime, such that G in here, such that transpose G j sigma of g equals j. So I really want to think of my quasi-split unitary group as living inside of GL2D, or rather its restriction of scalars. And in particular, it comes with a standard maximal compact open. It's just the obvious one that it inherits from the inclusion into GL2D. So call it KD. Inside the adelic points of F. So you just take HD of the adels and you intersect it. You just demand that the entries be everywhere locally integral. X prime, GL, 2D, O, F prime, completed at X. Okay. And so I want to talk about unramified automorphic forms. So, I mean, the theory of automorphic forms works the same way over function fields as it does over number fields, except it's a lot easier. Because, and everything from start to finish in this lecture is going to be unramified. There's going to be no presence of any ramification anywhere. So in this context, an unramified automorphic form on HD is just any function F on this discrete double coset space valued in the complex numbers. That's it. An automorphic form is just a function on that set. Okay? Now, I mean, in the last two lectures, there were all these generating series and special cycles and things that corresponded, that we were assembling into Fourier coefficients of Siegel modular forms or Hermitian modular forms. And so if we want to do something like that here, we need to talk about the Fourier coefficients of things like this. And so what we had these capital T's, these matrices T's that were either D by D symmetric matrices or D by D Hermitian matrices. And the analog in this context is not entirely obvious. So definition. I'm going to tell you what the T's are in this context. A rank D Hermitian vector bundle on X prime is a pair E, A, in which E is just a rank D vector bundle on X prime. And what is this A? Well, A is a Hermitian pairing on this vector bundle, but I want to allow the pairing to be very much degenerate. I mean, we have Fourier coefficients that were indexed by matrices T, but we allowed singular T. T could be 0. So I want my Hermitian form is going to be an OX prime linear map A. So it's a pairing on E that's going to be OX prime linear in the first variable, conjugate linear in the second variable. So I take E and I pull it back by my automorphism. That's complex conjugation into OX prime. And then you have to add in the usual Hermitian condition that if you swap the variables in the pairing, it puts a complex conjugation on the form. And the analog of that statement is, maybe I'll go over here. Such that induced map A from E into sigma pullback E dual, to give an A there is the same as to give an A there, satisfies, well, if I dualize A and then pull back by sigma, I get an arrow in the same direction. And I want that to be the same map. Okay. And now I'm going to just ask you to believe on faith a fact that I'm not going to explain, because it's not hard, but it's just sort of, I would write down a bunch of formulas and you'd say, okay. But fact, for an unramified automorphic form, it has a Fourier expansion, and the Fourier coefficients are indexed by these pairs EA. Okay? So fact, an unramified automorphic form, F, as on that board, has a Fourier expansion with coefficients F sub EA, they're complex numbers, indexed by rank D Hermitian vector bundles on X prime. So this is how we're going to talk about our automorphic forms, by giving their Fourier coefficients, which are indexed by these things. Okay.
So this condition is equivalent to having determinant 1, if it's determinant of Perry matrix?
This condition? No. I'm allowing A could be 0. I allow the 0 map. That would correspond to like taking the matrix T to be the 0 matrix. I'm going to allow things to be degenerate. Yeah, highly degenerate. This condition, it's the one over there that's OX prime linear. That says that it's linear in the first variable, conjugate linear in the second. This one is saying that if you swap the variables, it's the same as putting a complex conjugation on it. That's this condition. There's absolutely no condition of non-degeneracy. There's no choice. It's a double cover. There's a choice. It's the non-trivial one. It's a degree. It's a degree 2 Galois extension. Oh my God. That's because. Oh my God. Thank you. Good Lord. Oh, it's a double cover. Ay. Thank you. That's important. I wrote a 2 here, yeah. Okay, the coffee hasn't quite kicked in yet, despite this being my 5th cup, but I drink a lot of coffee. Okay.
I'm confused, but
yeah.
The Fourier expansion, I would have thought you would have restricted to a parabolic and then integrated only potentially.
Yeah, you do.
Imagine extensions of.
Yeah, but there's a way to simplify it, using the unramifiedness. Yeah. This is somehow, I don't want to write it out. I was surprised when I saw this too. It's written in the paper of Feng-Yun-Zhang where they define all this, and I was like, huh, what is this? But it works. But it's very specific to unramified automorphic forms. Okay. Theorem. So let's say this is due to Siegel, okay? He would probably not recognize it, but let's fix D and N, okay? And a rank N Hermitian vector bundle. So F, I'm going to suppress the A. I'm going to suppress the name of the Hermitian pairing, but I'm going to assume that it's self-dual. a rank n Hermitian vector bundle that is self-dual in the sense that the unnamed Hermitian pairing is this map that comes from it is an isomorphism. So I'm fixing an isomorphism. It comes with a fixed such thing. Okay, so to this vector bundle and this choice of D, you can attach a theta series. There is an unramified automorphic form theta upper F, like that. Okay, whose Fourier coefficients are the following. Fourier coefficient theta upper F sub E A. So this is for all rank D. For all rank D Hermitian vector bundles EA, it just counts the number of OX prime module maps from E to F. Such that the map respects the Hermitian forms in the sense that, so if this map is called I, then I can do E into F, which I have a fixed isomorphism to its twisted dual, and then I can do sigma pullback I check, and that maps to sigma pullback E check. And I demand that this composition be A. It just says if I take two sections of E, push them forward into F, and take the Hermitian pairing there, it's the same as if I took the pairing back in E. It respects the Hermitian forms. Okay.
Can I ask a stupid question?
Yeah.
So what would be a ramified automorphic?
Oh, it would be, an arbitrary automorphic form would just be a function on here that's right invariant under some compact open. But I'm taking the maximal compact open, that's why it's unramified, yeah.
Can I ask you,
Yeah.
pairs EA are just any, you're describing all points of the moduli space, right?
I'm not defining a moduli space yet.
No, but there's a bijection between pairs EA and elements of this double process. Am I right in thinking?
No.
No?
If
Or there's maybe an obstruction, a small obstruction.
if I was demanding, no, for one thing, the rank is wrong because HD is GL2D. But you're right that it is parametrizing self-dual Hermitian vector bundles of rank 2D.
Yeah,
But these are,
yeah, that's right. If you push it down to S, then it gets down to D.
Oh, I see. I think you're right. If I demanded that this map here was an isomorphism, like if it was actually a self. I'm allowing this to be very degenerate. It's allowed to be 0. If I demanded that this was always an isomorphism, then you're absolutely right. Then that would be a double coset space of that form. Yeah.
Oh, okay.
Yes. That's correct. Okay. Okay, there's now I'm already worried. Okay, I'll write it. So of course, there's a Siegel-Weil formula in this context.
Sorry, the concept of this theorem is just that it is left by invariant and zero?
The theorem is that there exists a function whose Fourier coefficients are given by these numbers that count embeddings of one vector bundle into another. That's the theorem. That you can assemble these coefficients into a function like that. I mean, I haven't told you exactly what the Fourier coefficients are. So sorry, I won't. I mean, it was in the first version of the notes, and it was a 2-page explanation, and it was, I mean, I could write it, but you'd still be unhappy. So I'd rather use my time, if you're going to be unhappy anyway, I'd rather use my time to say something else. So, that's life. Theorem. Siegel-Weil. If I take these theta series, and instead of fixing one self-dual rank n Hermitian vector bundle, sum over all isomorphism classes. Sum over f theta f. So this is for all. So this is the sum over all rank n self-dual Hermitian vector bundles on x prime. If you sum them, I should put in, like, I should divide by the size of the automorphism group of my vector bundle. But this is the value of an Eisenstein series. Value at s equals n minus d over 2 of an unramified Eisenstein series. E H S on HD of the Adels. Induced from the analog of the Siegel parabolic of my quasi-split unitary group. Okay? And the goal of this talk is to try to explain what happens when you take n equals d. So this has a functional equation and s goes to minus s. And when you look at the center of the functional equation, s equals 0, we want to understand, so we know what the value is. This gives a formula for it. What about the first derivative? I mean, the arithmetic Siegel-Weil formula from last time suggests maybe we can say something about the first derivative. Maybe in this function field setting, we could even get the second and third and fourth and fifth and sixth and all order derivatives. Okay.
You don't need to wait that sum.
Sorry?
You don't need to wait by the.
Yeah, I do. Yeah. Okay. Okay. That was the warm-up. Now here we go.
The expansion principle. In other words, the Fourier coefficients determine the.
Yes.
Unramified.
Yeah. An unramified automorphic form is determined by its Fourier coefficients. Yes. Yes. Okay. Yeah. Sorry? Yeah, that's a finite number. That's an infinite sum. So you have to take this with a big grain of salt. Just like in the last lecture when I stated the Siegel-Weil formula and I said something like for most d, because you have to worry about convergence on the left-hand side and poles of the Eisenstein series on the same thing here. You should take this more as inspiration. For exactly what choices of d and n this is literally true, I'm honestly not entirely sure. And exactly when the left-hand side converges, I don't actually know. So this theorem, this is definitely solid. This is really legit. That one, you have to interpret it a little bit. Okay, section 2, shtukas. Here we go. First, let's just work on the base curve x and not on the double cover. Because I don't want to assume that people have seen shtukas before. Okay, so here's a definition. Suppose f is any vector bundle on X. Actually, I want to now work. I want to base change X to the algebraic closure. Okay, a modification of F at a point X, a closed point of the base change, is another vector bundle G on xk bar together with an isomorphism between F restricted to, so I delete my point. I want a chosen isomorphism between my two vector bundles away from this point. So a modification at X is just, I've changed it and I've kept it the same except at X where I'm allowing it to change a bit. So the notation here, I mean, obviously, if you interpret it literally, it's completely symmetric in F and G, but I always have in mind somehow a source and a target. So I'm going to write it like this. A modification of F into G. Okay, now this gets its own board, I think. Okay, now I give you a definition due to Drinfeld. If you ask, why is this the definition? You can ask me, but I'm just going to say the answer is it's Drinfeld. That's why. I mean, it's definition. Drinfeld. I mean, one could say more, but a shtuka. Shtuka. On xk bar with R legs, or paws, I think. Maybe in French it's paws instead of legs. I don't. With R legs. I don't know what it is in Russian. With R legs is a chain of modifications. So you start at some f0, and you modify it at some point x1, and then you modify it at another point x2, and then you modify it. Oh, it's confusing. My dash. There are dashes, dash, dash, but then there are dots, and then there are dashes again, all the way to fr, modified at xr, and so these are going to be vector bundles on xk bar, modify, 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 and you modify it r times, and back at the end, you demand that you get back not the thing that you started with, but its Frobenius twist. At points that are not fixed, I mean, the points are part of the data. The data of a shtuka is the vector bundles, the points, and the modifications. At points x1 up to xr in x k bar. And okay, I mean, somehow on this x over k bar, there's somehow more than one Frobenius, depending on what you mean. But it means the Frobenius of k bar over k. As opposed to like the Frobenius on the structure sheaf of the curve. That's Drinfeld's definition. There's more than one could say about that, but instead, I'm going to say the following, just to try and help a little bit. You kind of have to trust that Drinfeld knows what he's doing, which is usually a safe bet. So remark. What is a shtuka with 0 legs? Shtuka with 0 legs is a vector bundle f on x k bar together with descent data. An isomorphism from F to its Frobenius pullback. But I mean, this is descent data all the way down to K. So a vector bundle over the base change with descent data is a vector bundle all the way down on K, i.e. a vector bundle on X. That's what a shtuka with 0 legs is. Okay, yeah, sure. I mean, yeah. Oh, yeah, I see. Yes, thank you. Yeah. So that seems reasonable, right? That's good. But then remark, and okay, I mean, if you're seeing this for the first time and you don't understand anything else that I say in my talk, you might benefit from just lying awake in bed tonight and considering the following remark, which I found extremely helpful when I learned this for the first time. A shtuka with one leg looks a lot like a lot, like a Dieudonné module viewed as a vector bundle on the curve spec of the ring of Witt vectors of FP bar. Curve. I mean, it's a one-dimensional scheme, and if you think about the definition of a Dieudonné module, the longer you think about it, the more and more it looks like one of these. Okay. So this would be a GLN shtuka, where n is the rank of the. They should have the same rank. I didn't write that, but a GLN shtuka would be a chain of modifications of vector bundles. I guess it's the being the same rank is built into the definition of a modification. So. But we want not just shtukas, but UN shtukas. So we have to do shtukas, but slightly more complicated, but not too much more complicated. So now, shtukas with Hermitian structure. So definition. So instead of an arbitrary vector bundle, now suppose F is a self-dual Hermitian vector bundle on our double cover over the algebraic closure of K. So now it has a perfect Hermitian pairing on it. A simple modification of F at a point x and x prime of K bar is I want to modify F to another vector bundle, again having a self-dual Hermitian form on it. But it's a restriction. If imagine you have like a Hermitian lattice over the ring of integers of a number field that's self-dual. If you make it a little bit smaller or bigger, it won't be self-dual anymore. So if you want to change it and get something that's still self-dual, if you make it a little bit smaller in one way, you also have to make it a little bit bigger in a different way. So a simple modification is a diagram where I start with my self-dual F, I have another self-dual G, and I have to have something, I'm going to make F a little bit smaller, and then make it bigger. So in which G is another self-dual Hermitian vector bundle, F intersect G, this is, if you like, it's just notation. It's another vector bundle. So my simple modification of F is going to be two more vector bundles related by a diagram like this. And the simple means that I'm changing it as little as possible while ending up at another self-dual thing. So if I want to change it as little as possible, that means the quotient F mod F intersect G should be really tiny, like a skyscraper sheaf supported at one point, X. And similarly, G mod F intersect G is another skyscraper sheaf, but supported at the conjugate point. If you start with something that's self-dual and want to modify it to something that remains self-dual, if you make it smaller at X, you have to make it bigger at the conjugate point. Think about that a little bit. And finally, F has a Hermitian pairing on it, G has a Hermitian pairing on it, and I want those to be compatible in the sense that when you restrict them to a Hermitian pairing on this vector bundle, they agree. So the Hermitian pairings. I mean, of course, the Hermitian pairing on the intersection won't be self-dual anymore because it's smaller, but Hermitian pairings agree on the intersection. Sorry? G is another self-dual Hermitian vector bundle. The intersection is another vector bundle which inherits a Hermitian pairing on it by restricting both of those, but it won't be self-dual anymore. It can't be. Yes, I am. I mean, of the same rank. Well, that's forced by, yeah. It has the same rank as F and G because the quotients are skyscraper sheets. Oh, in the skyscraper, I mean, yeah, like.
Copy of T-bar.
Yeah, exactly. Yes. Yeah. It's not obvious from the definition, but if you go back to the Shimura variety setting, this particular notion of simple modification is the analog of the signature n-1, condition. If you allow different kinds of modifications, it would be like putting in different signatures. But that takes a little bit of, you have to squint a little bit to exactly make that analogy, to make that precise. But now we can define the shtukas we actually want. So definition, a UN shtuka with R legs on X k bar, X prime k bar is a chain of simple modifications of rank n self-dual Hermitian vector bundles. F0 simple modification to F1. So I'm now going to use the same notation. Now, when I write this, we're in this setting. Whenever I write this from now on, F and G are self-dual Hermitian vector bundles, and a modification at X actually means one of these things. So simple modification at X1, simple modification at X2, down to FR, XR, and then you end up back at the Frobenius twist of the thing that you started with. simple modifications at sum x1 down to xr, x prime, k bar. Okay, Drinfeld doesn't really care about shtukas per se. He cares about their moduli spaces. Because Drinfeld was interested in the global Langlands correspondence over function fields, and if you want to prove the Langlands correspondence over function fields, at some point you have to produce Galois representations. And where does Drinfeld, in his Drinfeldian mind, imagine that these Galois representations might appear? He imagines that they ought to appear in the Étale cohomology of moduli spaces of shtukas. And he was right. There is a smooth Deligne-Mumford stack of dimension n times the number of legs that I'm going to call shtuka r un. This is over spec of our finite field, whose k-bar points are the un shtukas with r legs. You can form a moduli space of these things. I should think there are people who can't see past the computer screen, so maybe I'll do this.
So the definition of a family of theta would be similar, but we replace these k-bar points by r points.
Yeah, I mean, right, I only wrote it down over k-bar. I mean, if you did an arbitrary k-scheme, then you would have vector bundles on x prime base change to s, and these would be s-valued points. And you can, I mean, I'm only writing it on k-bar points for simplicity. Yeah, it's confusing enough as it is. And just as in this remark, a un shtuka with no legs is just a self-dual Hermitian vector bundle down on x prime. A shtuka with r legs on x k-bar prime is just a Hermitian vector bundle on x prime before you base change. Sorry? Well, I don't actually know about that. I mean, he certainly did GLN, but did he do it for any group? I'm honestly not sure. It's true, somebody did. What? That's possible. It's possible. Somehow easier just to credit everything to Drinfeld and not worry about it. Okay, so this is going to be, this moduli space is the analog of the unitary Shimura varieties in the last lecture. So where are the special cycles on them? Okay, so section 3. Feng-Yun-Zhang cycles. I started at 9:15. Oh, okay, so I have, yeah. Okay, no, that's good. I can do this. Okay. So, okay. In the first two lectures, this orthogonal Shimura variety and then this unitary Shimura variety, they each had a tautological line bundle on them. So is there a tautological line bundle on this moduli space of shtukas? In fact, yes. In fact, we have r of them, one for every leg. So on shtuka r un, there are tautological bundles. L1 up to LR. And I want to really think of these as living in Chow 1. How do you define it? It's actually, if you stare at the definition long enough, it's built into it. So I'm going to tell you at a k-bar point. So what does a k-bar point of our moduli space of shtukas look like? Well, it's one of these things. So maybe I'll just say, at a k-bar point, star, okay, if I have a k-bar point that looks like this, I'm going to tell you the fiber of L1. So I have to give you a k-bar line, a one-dimensional k-bar vector space. You go over here, and for the first tautological line bundle, I look at the first modification. And if you look at the first modification, here I have the target F1, and then a vector bundle sitting inside of it whose quotient is a skyscraper sheaf supported at a single point. And then the stalk at that point is a k-bar line. So I just take that, and that's the stalk of L1. It's a little confusing. At a point, the fiber of L1, say, is the stalk of the skyscraper sheaf F1 modulo F0 intersect F1 at the unique point where that skyscraper sheaf is supported, which is sigma of x1. I know it's weird, it takes a little time to absorb it, but sorry? Sigma of x1, because F0 mod F0 intersect F1 is supported at x, but F1 mod F0 intersect at F1 is supported at the conjugate point. In any case, and similarly, obviously, you just move along the modifications, and you get one line bundle for every leg. That's a little weird, but then the point is that, okay, instead of one tautological line bundle, we have R of them. So we can define script L to be their intersection in the Chow ring. So we have this sort of canonical codimension R cycle class on this moduli space of shtukas. Okay. So that's our tautological bundle, except now it's in codimension R. And now we need the analog of the Kudla-Millson cycles. Okay. Here we go. So this is going to take a little bit of time to write. But it starts to make more and more sense if you... Well, okay, let me write it. Definition. These are the FYZ cycles. Okay. We're going to fix a D between 1 and n. And these things, we hope to one day assemble, whatever these cycles are, we hope to assemble them as the Fourier coefficients of an unramified automorphic form valued in the Chow group. Which means whatever these cycles are, they should be parametrized by these pairs EA that I wrote down, the analogs of in this context, of our Hermitian matrices. So I'm going to fix an EA, and let's say a Hermitian vector bundle EA of rank D on X prime over the ground field. and I'm going to construct a cycle corresponding to EA. Okay. So let Z R E A of k bar. I'm going to define the cycle as a moduli space by telling you its k bar points. And this is going to be the set of maps from E. I'm going to take my Hermitian vector bundle on X prime, base change to the algebraic closure, and then try and map that into a UN shtuka, where this F bullet is shorthand for one of these guys. So a k-bar point is going to be a k-bar point of the moduli space of shtukas. And I want this map it should respect Hermitian forms. And what does it mean to have a map from this into this chain of modifications? It means this one fixed vector bundle maps into every element of the chain in a compatible way. So in other words, you form the moduli space of diagrams, i.e. diagrams. We've got our shtuka, x1, f1. So these are all vector bundles on x prime base change to k bar. f2, x2, fr, xr, which comes with an isomorphism back to the Frobenius twist at the beginning. And this one Hermitian vector bundle, base change to k bar, should map into each one of them. In a way that respects Hermitian pairings. And at the end, this vector bundle of rank D was defined over x prime with no base change, which means it already comes canonically identified with its Frobenius twist. It already has descent data. And so I'm going to call this T0, T1, T2, TR. And this TR should be compatible with the T0. It's the Frobenius pullback, the T0. The map we already have here. It's a lot, I realize. But I mean, it might be helpful to think back to this, the moduli theoretic definition of the special cycles on the unitary Shimura varieties, which were the moduli theoretic definition was I had an abelian variety. Okay, if you believe that a shtuka with one leg is kind of like a Dieudonné module, then you should believe that a shtuka with one leg is not so different from a p-divisible group or even an abelian variety, just an abelian variety with more legs. And so this is kind of like an abelian variety, and this is kind of like an elliptic curve, except that analogy only goes so far, because if we're really like an elliptic curve, then this ought to have modifications in it too. So why aren't I modifying both of them? And that goes back to the fact that in order to get this moduli interpretation of the UN Shimura variety, I had to pass to some Ital cover, which was coming from a different Shimura datum. So it looks a little bit like the moduli interpretation in the Kudla Rapoport case, but not quite the same, which has to do with the fact that back in the Shimura variety case, there was actually more than one Shimura datum associated to a Hermitian space, and we weren't quite working on the one that has a moduli interpretation. If you squint a little bit, it looks like the definition from last time. If you stare too long, it starts to look different, and there's a reason for it. So let's not stare at it for too long. Let's just say it's a definition. Oh, be the set of maps. It's a definition / theorem. This is represented by a cycle, you can form a moduli space of these things. Z, R, that's too fancy a Z. Z, R, E, A. If I forget all of these maps and just take the shtukas, I get a map down to shtuka R, UN.
Can I just ask?
Yeah.
Are your modifications xi simple?
Yes.
Okay.
Yeah. It's built into the definition of a UN shtuka, a chain of simple modifications.
It's a chain. Oh, sorry.
Yeah. Yeah, yeah. So I'm base changing it, yeah. And I'm telling you the k-bar points of this stack. Of codimension, okay, so if you remember both in the Kudla-Millson theory and in the Kudla Rapoport theory in the unitary case, we sort of, if we start with a self-dual, not self-dual, but a Hermitian vector bundle of rank D, this would be like a D by D matrix, and we would be looking for a cycle of codimension D, but it didn't quite come out to be the right codimension. It was the rank of the matrix, so it was a little bit smaller, and we had to correct it. Same thing is happening here. The codimension is now R times the rank as a vector bundle of the image of, the rank has to do with the degeneracy of the Hermitian pairing on E. So you look at this, the Hermitian pairing, we're expressing as a map from E to sigma pullback E check. The image of that map is a sub-vector bundle. You take its rank as a vector bundle and multiply it by R. So this is the analog of the rank of the matrix T if you believe that EA is like a matrix T, which is at most R times D. So the codimensions of our cycles always come out to be multiples of the number of legs. It is finite and unramified, which is good enough for government work. Also, this is not true. These things are usually not equidimensional. So this statement that it has this correct dimension, you have to interpret it in some appropriate derived sense to do this. Okay, but even, I know it's all crazy and weird looking, but hopefully the next step is going to look familiar, because we wanted a cycle of rank R times D, and we came off a little bit, but we came off, our error is a multiple of R, but we've got this codimension R thing floating around. Codimension D, so can define a kind of corrected version, CREA. To be, you take this cycle, ZREA, and you intersect it in the Chow ring with enough copies of this guy to get into this codimension. So enough copies to get a cycle of codimension R times D on the moduli space of shtukas. These are the analogs of the Kudla-Millson cycles. I'll just pause for a moment. I think I've got 20 minutes, and I think I can do this. So this would be a good place to ask questions, or not if you're just completely lost. Or in the previous lectures there was an L inverse. It's just notation. I probably should have defined this to be the intersection of the inverses of these. It doesn't matter. It's just. The L here is constructed, it's analogous to these L's are analogous to the inverses of the tautological bundles in the previous lectures.
Okay, I have a
Yeah.
question. So you also have other natural bundles where you do like F0 over F1 intersected with F0. And this will be the
F0 over, well, that one comes out at the end because, we kind of wrap around. So that one, it's sort of, you're saying, why didn't I have an L0 here? or something. I mean, I've defined only L1 by doing this one. So then I can bump up all the indices by 1, and that would be L2, and so on.
I think the question is that you have two Schrader sheets.
Yeah. They're in duality, so you don't get anything new. Yeah. I mean, I think if you were really going to be picky and try to say what is the analog of the tautological bundle from the previous 2 lectures, it would be the one that you said, the one coming from this skyscraper sheaf. But it's dual to this one. And then we're keeping track of this one, and that's why there's no inverse here. So, I mean,
Usually one doesn't impose that the modifications are non-speak, so it's...
Right. That's why I said this particular notion of modification is the signature N1 condition. I really want... I mean...
Oh, well, that's it.
I mean, I want a minuscule co-character because I want something that looks like the Shimura variety, right? So.
But you can make it, I mean, you could just draw this definition and you would get a bigger space.
Yes.
So that's for this.
So your definition of cycles, what do you mean by respect to the addition form?
I mean that if I took 2 sections here and paired them, I would get a function on my curve. It would be the same as if I applied this map to get sections here and took the Hermitian pairing here. Okay. So maybe you can start to see where this is going, or maybe not. There's a conjecture. Of Feng-Yun-Zhang. Those are the Fourier coefficients of an unramified automorphic form valued in the Chow group. For any pair of integers n and d, the cycles as E, A varies over all Hermitian vector bundles of rank D on X prime are the Fourier coefficients of an unramified automorphic form valued in the Chow group, which means nothing other than a function, CR, on our double quotient. Valued in codimension RD, Chow RD, shtuka RUN. They conjecture that there exists a function on this space valued in the Chow group such that when you take its Fourier coefficients, you get these cycles. You can assemble them into an automorphic form. Okay? Sorry, louder.
Where would they expect?
Because it's the exact analog of the Kudla-Millson modularity theorem. That's the answer.
Yeah, I can see.
And if you take 0 legs, it's the theorem of Siegel that I stated at the beginning on the existence of unramified theta series. That's when r equals 0, this is not a conjecture, it's a theorem, which I kind of jokingly attributed to Siegel.
And then when R equals 1, was this already known by virtue or something, or did you only work in?
Not in the function field case, no.
Okay.
When R equals 1, it's still an open problem.
Okay. Oh, so
When R equals 1, it's an open problem.
okay.
They have a result that says this becomes true if instead of on the entire moduli space of shtukas, you pass to its generic fiber. But, and pass to cohomology, but then in the Chow group, the theorem in the generic fiber is due to Feng and Adil Khan. I'm not going to write that. It's just... Okay. In the Siegel theta function, yes. When R equals 0, you get the Siegel theta function. Or kind of a refined version of it, because when R equals 0, it's actually slightly stronger, because you're working in the... Okay. You would have to take... Okay. If you took R equals 0, you'd have some moduli space here, but you'd be working with 0 cycles, and you'd apply the degree map on those 0 cycles. And when you apply the degree map to get something scalar valued, you'd get the thing that I wrote down and attributed to Siegel. Yeah, yeah.
And when you put that to the generic fiber, you mean to the generic fiber of the other?
Oh, right. I mean, there's leg maps down to R copies of the curve, and you take the generic fiber of the product. Yeah. Okay, section 4, Siegel-Weil, again. So now we're going to take D equals N. This is stronger. You could just, you could pass to l-adic cohomology of the moduli space of shtukas, and if this is true here, then it remains modular after you pass to cohomology. Is the conjecture known? No, it's the cohomology of the generic fiber of the moduli space of shtukas. So something is known, but not as strong as what you're asking. When we take D equal N, then for all rank N Hermitian vector bundles EA on X prime, we get a 0 cycle. Because we're in codimension Rn, and if you remember, I stated this theorem of Drinfeld, which included a statement about the dimension of the moduli space, and that was it. So we're in top codimension. So we'd be looking at 0 cycles. Oh, it's right there. Yeah. Yep. Dimension Rn. Okay, so we take D equals N, we get 0 cycles, and here's the theorem. There is an unramified Eisenstein series. It's the same one that appeared in the Siegel-Weil that I stated at the beginning of the lecture. An unramified Eisenstein series. EHS on our quasi-split unitary group, but now D is N. Such that for all of those guys, the degree of this special 0 cycle is you take the EA Fourier coefficient of the Eisenstein series, you take its rth derivative at s equals 0, and it's this. dr by ds r e a of s evaluated at s equals 0. So this is the EA Fourier coefficient of the Eisenstein series. I didn't mean this. Don't know it for all EA. Whenever, so the original theorem of Feng-Yun and Zhang, whenever EA is non-degenerate, so this is the analog of det T non-zero, non-degenerate in the sense that the Hermitian pairing on this vector bundle is injective. Okay. And in joint work with Tony Feng and Mikhail Merkjan, yeah, Jan can rattle off coefficients of the J function, and I struggle with my co-author's name. M, R, K, T, C, H, Y, A, N. Not Mr. Kitchen, Merkjan. It's true in the next case, where it's not injective, but the kernel is a line bundle. EA has co-rank 1. In the sense that the kernel of A is a line bundle. So in other words, the Feng-Yun-Zhang case is the case where there was no correction term. The corrected cycle is the Feng-Yun-Zhang cycle. The co-rank 1 case is the case where you have one correction term. You're off by one copy, so you have to take the naive thing, intersect it with this tautological codimension R thing to get a zero cycle, which you can then compute and match up with the derivative of the Eisenstein series. Now, of course, one conjectures, or one would like to conjecture, that this is simply true for all EA, which would say that this conjectural, in this case where D equals N, you take this conjectural automorphic form and you would just apply the degree map to it. It would say you just get the Rth derivative of an Eisenstein series. There's an issue here, which is that this moduli space of shtukas is essentially never proper. It's proper when N is 1. But because it's not proper, this degree map, there's not actually a degree map on here. But you can ad hoc your way out of it a little bit. In these two cases, the underlying Feng-Yun-Zhang cycle is actually proper over K, which allows you to upgrade the cycle class to something in the Chow group with compact support, which has a degree map on it. So under these two assumptions, this degree is actually a well-defined thing. But when you get past these two cases, there's no expectation that the Z cycle has proper support, which means we don't actually know how to formulate the conjecture beyond these two cases. So, I have 5 minutes. And the title of my lecture series, which I did not choose, is Algebraic Cycles and L Functions. And there have been no L functions. So I have 5 minutes to fix that. So this should be interesting. There's something that I've been wanting to say all throughout these lectures, but kept running out of time.
I think you are the only one who didn't change the title.
Oh, really? I should have just said algebraic cycles. Let's see what I can do here. L functions. Oh boy. The abbreviated version. Okay, we're going to switch the picture a little bit. So, well, actually, okay, go back. So here D was N. So let's go back to any codimension. assume the modularity conjecture. Of Feng-Yun-Zhang. Assume we have this unramified automorphic form valued in the Chow group. Well, if you have two scalar valued automorphic forms on the same group, you can take their Peterson inner product to get a scalar. If you have an automorphic form valued in the Chow group and another automorphic form that's scalar valued, you can take their Peterson inner product to get an element of the Chow group. So given any cusp form, F, unramified, any unramified cusp form on HD A F, we can form what Kudla would call an arithmetic theta lift. So I take that conjectural automorphic form, maybe I'll write CR of F. It's going to be the integral over the adelic points of our group of this cusp form against this Chow group varied automorphic form of Feng-Yun-Zhang. Oh, that's bad notation. Let me call it theta. Chow RD. If you're worried about convergence, it's a famous theorem of Harder that cusp forms are actually compactly supported. So actually, this is a finite sum. And if my cusp form has complex coefficients, maybe I should tensor the Chow group with C. But okay. Okay. So now let's restrict to the special case where n is actually 2d. So these cycles are in middle codimension. The expectation. So this is the Rallis inner product formula, which I wanted to talk about last time. So let pi be a cuspidal automorphic representation of HD. And take unramified vectors, f in pi. Assume that it's an unramified automorphic representation. Fix a cuspidal automorphic representation. Then take n to be, fix a d, let pi be a cuspidal automorphic representation of this quasi-split unitary group. Then take n equals 2d and form the Feng-Yun-Zhang generating series. And then take the Peterson inner product between these two cusp forms and the Feng-Yun-Zhang generating series to get two classes in the Chow group. The expectation is that so now I can take this theta lift with r legs of the form f and this theta lift of the form in the dual representation, intersect them in the Chow ring, and because they're in middle codimension, I end up with a zero cycle in the Chow group, and I can take its degree. And the expectation is that this is the Arth derivative of the nth derivative at the center of the functional equation of the base change L function of this automorphic representation times some local factors depending on f and f dual, which is if these unramified vectors exist in this automorphic representation, then they're unique up to scaling. So you have to correct for the choice of scaling factors in some way. So there's going to be some local factors depending on f and f check. Okay? And I am now, 2 minutes over? I'm going to go a little longer over, but don't worry. Okay, there's an L function. It's the base, an automorphic representation on a quasi-split unitary group has something like a standard L function. It's the base change L function. Sorry? The normalization, yeah, sorry. I meant S equals a half. That's what you meant. Okay, thank you. Why would one expect this? Okay, because this Eisenstein series that appeared in Siegel-Weil also appears in a Rankin-Selberg style integral called the doubling integral, and the doubling integral is an integral representation for this L function. And so if you do a sort of formal calculation, and ignoring the fact that the reasons I already explained, this degree is not quite well defined, you would expect this in the number field setting. This is a theorem of Chao Li and Yifeng Liu. And no, only for the first derivative. Yeah, sorry. Yeah, only the first derivative. And there's a version for p-adic L functions due to Daniel Desaigne and Yifeng Liu. And one would like to do something like this in the function field setting. One would like to prove this. But the obstruction of, first of all, like I said, this degree is a little bit sketchy. And if you wanted to prove this, you would really somehow need this for all coefficients. So in my remaining -5 minutes, I'm going to state the best we can squeeze out of the theorem that we actually have. Okay? So here it is. You have to temper your expectations a bit, because we want an actual theorem and not wishful thinking. And so here's the theorem. So this is Feng, M A car M K T C H Y A N. Take d equals 1 and n equals 2. So what does this mean? Now we fix an unramified cuspidal automorphic representation pi of h1, which is the u11, over our function field. Assume the Feng-Yun-Zhang modularity conjecture in middle codimension in this setting, which Tony assures me he knows how to prove. But it's not written down. Assume f, y, z modularity in this d equals 1, n equals 2 case. So Tony says, okay. He's a pretty careful guy. Then, okay, we can't prove this, because it doesn't make sense. You're just stuck with the fact that this arithmetic theta lift always lies in this Chow group and doesn't have a distinguished lift to the Chow group with compact support. So we don't even know how to make sense of this. But if you take the theta lift on one side, and on the other side, fix any cycle in middle codimension with proper support, like this, then there's an intersection between the bare Chow group and the Chow group with proper support into the Chow group with proper support, which has a degree on it. Which means I am allowed to make sense of if I take any rank 1 Hermitian vector bundle E, A on x prime, and don't do something dumb like take A to be 0, then the corresponding cycle will be proper, which means I can form the arithmetic theta lift. So take an F, an unramified vector here, and I can intersect it, the Chow ring, and the Chow ring with proper support, where this guy lives. This will live in the Chow group of 0 cycles with proper support, and so there's a well-defined degree on it. And the theorem is, you get pretty much what you want. You get the rth derivative of the base change L function for any r. Evaluated at s equals 1/2. But then there's some correction factor, which has to remember both which f you chose and which naive cycle you're pairing against. And the correction factor is you take the form f and you take its EA Fourier coefficient. And that's the theorem. I went way over. I apologize. I'm very much done. Thank you.
Questions?
It's a lot. Let's start at the front and work back. Yeah.
I'm not very familiar with the paper of Yun-Zhang, but I seem to recall
The
that
Gross-Zagier one, you mean?
yeah, they first prove a higher Gross-Zagier before having a higher Siegel-Weil formula.
Yes.
So they can't use this Rankin-Selberg method. So
That's right. They use a trace form. There's no Rencontres. It looks
Okay.
very different from the original Gross-Zagier proof. The Yun-Zhang paper is based on the relative trace formula. Jacquet's relative trace formula proof of Waldes-Breget's period formula. And so there is no Rencontres integral. There's no Eisenstein series in their paper. Yeah.
Okay.
Very different.
It's okay.
A little louder. Sorry, I'm old. Go ahead.
There's already been some questions about this, but I guess I don't really understand the geometry of like this locally symmetric space wall over a function field. So could you
Oh,
just
you mean the moduli space of shtukas?
No, the modular space of like 2D vector model. I mean, just like the quotient HD of AF.
Oh, I mean, it's just I don't know what to say about it. I mean, it's a discrete set.
I guess my question was like on the Fourier coefficients.
You want me to say how you attach Fourier coefficients to an unramified automorphic form?
Yeah.
No, because it's two pages of notes that I left in my room, and I'm looking Feng-Yun-Zhang. Yeah, I'm not going to say how to do it. Sorry, not going there.
I guess that's an answer.
Or if you want a shorter version, I wrote it sort of in preparation for doing this. I wrote a short paper with Yang-Yi Chen called, I don't know what it's called, but it's the only paper I have with Yang-Yi Chen, and we wrote it out carefully for my benefit. So you can look in that to see this. Right?
Is it known how to regularize the left-hand side? This tag.
Regularize.
Just to your left. There. Yeah. No. There.
Here?
Yeah. When it's, the non-compactness problem.
I don't know how to overcome the non-compactness problem.
Okay.
The point is that, I don't know what this actually
The
means.
conjecture is not well defined for now.
No.
Yeah.
No. But if you put in something with proper support,
Yeah.
it makes sense. Yeah.
Yeah, so it's a very naive question, but the cycles in the moduli space are all defined over K.
Yeah.
Is there any way of passing to an integral model, whatever
This
that
is the
means.
integral model.
Oh,
this,
this is
this moduli space of shtukas is the function field analog of an integral model of a Shimura variety.
Okay. And can you do like any analog, like Kellogg theory on this? Or
No, it's easier. It's
Oh.
somehow because it really is just like you can just work with the Chow group. You don't need arithmetic
You don't
Chow
need
groups. There is no arithmetic anything because there are no Archimedean places. The bad side is that these moduli spaces of shtukas are compact far less often than the Shimura variety analogs. So you win some, you lose some.
I want to if I understand something correctly. So in the Shimura variety case, the Eisenstein series and the L function are different depending on if R is equal to 0 or 1. But here they're the same
Yeah.
independently of R.
Yeah.
That's a difference. Do you have anything?
No, you're absolutely right. That it's because somehow in the Archimedean setting, there's somehow two flavors of Eisenstein series. I mean, it's the Eisenstein series in Siegel-Weil, where you're looking at a central value, and the Eisenstein series in arithmetic Siegel-Weil, where you're looking at a central derivative, both depend on some everywhere local data. And the everywhere local data that goes into defining those two Eisenstein series is the same everywhere except at the Archimedean place. You get two different Eisenstein series by changing only the Archimedean data. In this setting, there is no Archimedean data to change. You only have one Eisenstein series.
Thank you.
Sorry. So, I mean, you're very knowledgeable about both the function field case and the original case. So, seeing this result for like higher derivatives, I guess the obvious question is, okay, what can you say now about the second derivative? Like, what's the moduli space of shtukas with two legs over what is like Z?
No comment. You're asking me how to import this back into the Shimura variety world. I have nothing to say, nothing.
Okay, thanks.
Okay, maybe we can stop the questions. You can ask further questions to Ben. He has the energy. And we can thank him again for this one.